Hello and welcome back to The Space Between, one of the top astronomy podcasts in the world, and for that matter, the universe. My name is Kolby Van Camp here with Dawson Wagner, and wherever you're tuning in from, whether that be Germany, Finland, India, the US, or wherever you are getting this podcast from, we're glad that you're here and that you're joining us in The Space Between. With some business to share with you, we've updated our cover art. We wanted to take out our look and move it up to the next level as we continue to expand our content for you. So let us know on social media what you think. You can DM us at SpaceBetweenPod on Instagram, or you can send us a message on Facebook. You can also follow us on TikTok at SpaceBetweenPod as well. By the way, be sure to follow us on all of those platforms. And while you're at it, be sure to give us 5 stars on any of the platforms that you're listening on and leave a quick review because we want to hear from you. Before we jump into our interview, we want to remind you that we're trying to come up with a name for the fan base. If you're listening on Spotify, there's an interactive feature connected to the episode where you can provide your answer. Just swipe down. Boom, there it is. Type in what you want, the fan base to be named, and we will connect with you further. If you don't have Spotify but want to be in on the action, no sweat, just hit us up at our brand new and improved, fully functional website, www.spacebetweenpodcast.com. Reach out to us, people. We don't hear enough from you. You can also join our Quantum Computer Discord server through our Patreon to chat with us if you want to connect with us in that way. So just shoot us a message on Facebook, DM us on Insta, join our Discord, whatever you want to do. Let us know if there's a topic that you want to hear about or an expert that you want to hear from, and we will try and set that up from you. Also, in case you already didn't know, we're starting to exit galaxy season, but that means one of our biggest friends in the night sky, the Orion constellation, is starting to hit the skies here in the Northern Hemisphere, and that means that I'm going to be investing in a range of new gear to get my best photos to date of the Orion Nebula, the Horsehead Nebula, and the Greater Barnard's Loop that's in the Orion constellation. I'm going to be frequenting High Point Scientific, and I suggest that you do too for all your astronomical needs. Visiting the link in the description of this and every one of our episodes for your purchases will provide us with a small commission, which not only helps Dawson and I continue to make technical improvements for the show, it helps us make technical improvements to our astrophotography as well. It's my distinct pleasure to introduce to you Dr. John Mather, Nobel Laureate in Physics, Senior Astrophysicist for the James Webb Space Telescope, member of the National Research Council, cosmologist, and so much more. The list goes on and on. Dr. Mather, it's an absolute pleasure to have you on the show today. Thank you for taking time to sit down with us.
I'm happy to talk with you and with our audience.
Yeah. So first of all, I wanted to jump right in and ask you, you shared a lecture on the campus of Kansas State just a couple of weeks ago, which is how we got connected because Dawson and I are graduate students at Kansas State. You come from a family of scientists and thinkers. Why astrophysics and cosmology? Why not medicine or a social science or some other scientific route?
Oh my goodness. Well, how do choices get made when you're 7 years old? I have no idea. But I do remember looking up at the sky. I do remember seeing the Museum of Natural History with the planetarium show in New York City. I saw the dinosaur bones and the exhibits about volcanoes and electricity and TV shows about science. And somehow I latched onto astronomy and physics as the coolest thing. So gradually I learned how to make electronic circuits and build telescopes with cardboard tubes and lenses. And it's just grown from there. So I do not know how I chose.
So you shared that you and George Smoot won the 2006 Nobel Prize in Physics for your work on the Cosmic Background Explorer and its work on studying the cosmic microwave background. Would you briefly break down Kolby and the importance of its work on solidifying cosmology as a precision science and why it won the Nobel Prize to begin with?
Sure. Well, to begin with, we know the universe is expanding because we've seen galaxies rushing away from us at enormous speeds, and we've known this since 100 years ago. And we now have a story that says there was something we call the Big Bang, which is a rotten name for the thing we actually saw. And so could we measure the trace remnants of those early times? So it was predicted that the universe should be filled with the heat radiation of those very, very hot early times. And it is there. It was discovered in 1965. And so right away, it was clear that we had to measure it better. So I started off with a thesis project in Berkeley to measure it better. And that project failed. But I got a job at NASA in New York City. And shortly after I got there, NASA said, we want proposals for new satellite missions. We want to do some science now that we landed on the moon. Okay, boss, my thesis project failed. We should try it in outer space. We wrote a proposal and it was accepted eventually, and we built it. And 15 years later, it flew. So what did we do? We measured that cosmic heat. Two important things about it. One is, what's the color? Does it have the color that it should have if it comes from the early universe? And the answer is yes, it does. Within about 50 parts per million, it's perfect. So who knew that we could do that well? But it was our idea of how to measure it that did that. So that was a direct outgrowth of my failed thesis project. The next thing to measure was, is it equally bright in all directions? Answer is no, not exactly. And we published a map that has pink and blue blobs all over it that shows where the sky is brighter or fainter than the average. So how bright is the sky? Well, it's a temperature of about 2.7 degrees above absolute zero, which sounds awfully cold, but it's actually most of the. So can you measure it better? Well, yes, very, very carefully. So our map shows these blobs that show areas that are 30 microdegrees warmer or colder than the average. So 100 parts per million. So Stephen Hawking saw the chart and he said, that's the most important scientific discovery of the century, if not of all time. Oh, wow. So Stephen, why is that so important? Here are what I think he meant, because he's not here to ask anymore. So number one, we wouldn't be here if there were no spots in that map, because we depend on gravity to stop the expansion of the cosmic material and turn some of it back and pull it back together so we can make stars and planets and galaxies and everything that we see. So we're here because of those spots. Number two, most of them come from cosmic dark matter. We deduce that it's there, but we can't see it. The pattern is affected by cosmic dark energy. And again, we deduce that it's there, but we can't see it. And the fourth thing really is, if you could ever figure out what made the spots, maybe you'd have a clue about quantum gravity, which is one of the biggest mysteries of physics. Quantum gravity suggests that maybe space and time aren't even fundamental, and they themselves are uncertain, chittering around. Okay, so that is the combination of the three weirdest things we've got to think about all in one map. So pretty important. So we measured that, and it was confirmed later on by more measurements from the ground and more satellites in space. One that we did at NASA Goddard was called the Wilkinson Microwave Anisotropy Probe. So it got the same answer, only better. So, okay. Yeah, that's how come we got to go to Stockholm.
Okay. That's really cool. What about your master's thesis caused it to fail? Was it because it was on Earth, you needed it to be in space, or were there other reasons for that?
Yeah, actually, it was a doctorate thesis, and it was a balloon payload. It was what I call a satellite on a string. So you get as high up above the Earth's atmosphere as you can. And so that's the closest you can get to space without being in space. And what caused it to fail was it's cold up there. So we had two things that failed just because it was too cold for them. And a third thing that failed was the motor rusted up because it got wet on the ground. Okay, so we knew the general idea was right. But,
okay.
So that's how we got to fly these two astonishing experiments on a real satellite way above the Earth's atmosphere.
Very cool. Very cool. Dawson, I'm going to turn it over to you for your question now.
Yeah, I'm just so curious. You know, you talk about satellites and the things that you've been able to work on. My favorite satellite being, the James Webb Space Telescope, and it launching within the last 2 years, and your kind of experience as being a part of that. Since I know you talked a little bit of this at the lecture here at Kansas State, but since the launch and the process of that, what has the dynamics been with the turning over of the reins and kind of allowing and teaching others the process of what you kind of helped start as one of the senior project scientists?
Oh my goodness. So handing over the reins, it's not quite exactly the word.
Okay.
Teach people things that you don't even know how to do. So basically, we recruit scientists and engineers, and of course, most of the team are engineers and technicians and not scientists. But we recruit people and we say, here's the job to do. Can you figure out how to do it? And so we the science teams say, well, we need it to be this big and it's this good. this sensitive, and you work at these wavelengths and have these characteristics. And then we work with engineering and technical teams to say, oh, well, I could do it this way, or I could do it that way. And which way do you prefer? And so it's conversations for years to figure out what to do. And then when we come to handing over the reins, as you call it, basically it means other people are already ready and already doing almost all of the work. And so the way you're already doing it. So it doesn't really mean a change. It means, okay, different people go to the meetings and we still do the same work.
Right, right. No, that makes sense. Keeping it consistent, and that it's not there's not a lull in between the transition of leadership, and so that's affirming as me, someone who's very passionate about understanding what's happening with the James Webb Space Telescope. How are they keeping tabs on it, and checking in who's overseeing that. What are some of the things that maybe you could share about the sensors, maybe on board of the James Webb Space Telescope? I know infrared sensors are the most commonly heard, but are there any other sensors that maybe help it work and in the process of making it capture the things?
Yeah, so of course we've got the cameras and spectrometers, which is the infrared sensors that you're thinking about, that we record the light coming in from the space, and we make a picture, say, well, this is what you would see if your eyes could see infrared wavelengths. So that's the sort of workhorse cameras. And by the way, we cover wavelengths that range from 0.6 micrometers, which is red, and you could see that with your eyes, out to 28 micrometers, which is a lot longer, and you certainly couldn't see it. So there's a whole collection of astounding semiconductor technology that makes that possible. So a light wave comes in, a photon of light excites an electron in the semiconductor. We move that electron around. Eventually, we can count it, and then we say, okay, send a signal back down to Earth. A little bit of light came in. So that's a sort of infrared version of what's in your telephone camera, but it's basically the same idea. So that's turning the light into pictures, is that part. You asked about other sensors, and of course we do need a few others. We need to know where we're looking. So we have gyros to tell if we're spinning and rotating. We have accelerometers to tell whether the rockets are pushing. Those were mostly needed for the initial launch, of course. We have sensors to tell, are we staying pointed in the right direction? So we've got something like crosshairs. If you wanted to aim something else, you'd have, I see a star over there. I want to put the image of the star right on the crosshairs of my eyepiece. So we have the equivalent of a camera that does that. So that's called a fine guidance sensor. And the combination of all these things are what we use to keep the telescope pointed at something for a long time. So it's interesting you ask about that, because the whole system is a whole lot more complicated than just taking a picture. You have to point at something and know where it is in the sky.
Right. And the data collection then that comes back from that, what kind of frequencies do you guys use to be able to send that information all the way from the Lagrange point back to Earth?
Yeah, so we use two microwave bands. S-band is called. It's around 2 gigahertz, I think, to send commands up and down. And we have a higher data rate link called Ka-band. I think it's around 19 gigahertz or so. So we can get the data back a lot quicker that way. So it takes quite a few hours every day of contact between this telescope and the ground stations here on Earth to get all the data back. Because we take a lot of pictures.
How many ground stations on Earth are there around the Earth? Because it's not just the United States that's always pointing at the telescope.
Yes, well, we have 3 main ones that we use. One in the Mojave Desert, one in Australia, and one that gets a little less use near Madrid, I think.
Okay.
So we need them in 3 widely separated places.
Cool.
And so those are the main ones.
Very cool. So for you, in your mind, what's the most important work that James Webb Telescope is currently doing?
We are looking at hundreds of different things. Every year, people send us over 1,000 proposals for the coolest things there are to look at. And we have a long discussion in a committee, and we choose a couple of hundred. Okay, you, and you. So which ones are the most important? Well, there are 4 main themes. what is the first thing that happened after the Big Bang? When did the first objects grow? So I talked about the pink and blue blobs. That was before there were any stars and galaxies. Well, how did the first ones turn up? And in particular, were there any black holes originally, or did they grow later? Every galaxy seems to have a black hole in the middle now, and we don't know how that happened. So which came first, the galaxy or the black hole?
Chicken or the
That's
egg.
one of the hard topics, and we're working on that. And so how far back in time can you look? That's one of the things to try. So how do you look back in time? You look at things that are far away, because light travels at a high speed, but it's not infinite. So you can say, I looked a billion light years away, so I'm looking a billion years back in time. So, okay, so that's how we look back in time. So we see the universe as it was when it was young, and we are getting close, not very close, but closer to the first moments. First objects we've found are about 100 or 200 million years after the expansion began. So that's a whole lot different from today, which is 13.8 billion. So it's back to when the universe is about 1% as old as it is now.
Wow.
It means 10,000 times as dense. Everything was completely different in those early times. So that's a slight fascinating story to tell. It's a little difficult to work out. We have been surprised and surprised and surprised because we just did not know what to expect. When we built the Hubble telescope, it was thought, on good reason, that we would see the first galaxies growing because we could see far enough back in time. We were so wrong. So it's hard enough to do it now, even with this much more powerful telescope. Because, anyway, that's one of the hottest topics. When did the first objects grow? So the galaxies, did they grow from little pieces that were formed into smaller bunches and then those come together, or is it formed all at once? So it's beginning to look pretty. A good explanation is it formed out of lots of little pieces that were formed first and then they fell together. So that means, for instance, our Milky Way galaxy that we live in here has lots of satellites, lots of satellite small galaxies. We still have two. They're called the Large and Small Magellanic Clouds, and you can see them in the southern hemisphere. And they're beautiful and bright. And those are the only two we still have left that are still falling in. So that's one of the big stories to tell. We do see that other galaxies are often colliding with each other and merging with each other. So this is a very dramatic story. Indeed, the Andromeda Nebula, which is the nearest big one to us, is going to come and hit us in about 2 or 3 billion years. And that's pretty exciting, except we won't be here then. But a great cosmic collision of two galaxies. So then how are the stars born? Well, in the beginning, there were no stars. Then there was the first generation of stars, and they were probably different from any that are happening now because the primordial material was very dense and it had only hydrogen and helium in it. Nowadays, it's all different. The first generations of stars blew up and exploded out with heavy elements, carbon, oxygen, nitrogen, phosphorus, calcium, all the stuff you see around you in the house. That was formed inside stars. So that clearly affects the way new generations of stars are being born. So, our sun is actually pretty much of a newcomer. The sun is only 4.5 billion years old, and the universe is 13.8. So many generations of stars came and went before the sun was born. So now we get to the question of how do you see this? And we see beautiful clouds like as you've seen the pictures, the pillars of creation, the cosmic cliffs, other beautiful spots, the Andromeda Nebula, where new stars are being born as we speak. So we're looking at them. We use the infrared capability to see through the dust clouds inside to where the real activity is happening. So, and then finally, how about those planets? We live on a really lovely little planet called Earth. So far, it's the only one like it. So that's both exciting and terrifying. So clearly everybody wants to know, are we alone?
Yeah.
And the astronomy part says, well, planets the size of Earth and the temperature of Earth are very common. About 1 star out of 5 has them. And most stars have a lot of planets. So anyway, there are a lot of potential places. We do not yet have the capability to look at another Earth around a star like the sun to see, well, do you have an atmosphere? Are you blue? Do you have oceans and continents? So not yet. So far the answer is we've got lots of planets. Little ones, little rocky ones are bare. They're only rocks with no atmosphere that we can see. Big ones are like Jupiter and Saturn and Uranus and Neptune, and they are mostly gas and have lots of interesting chemicals in them. So we know the technology that we're using works, but we cannot say, see, I found another Earth over there.
How close are we to that, you think?
We don't think we can do that with this telescope.
Oh.
It's not a good enough tool. So, of course, that leads on to what are we going to do next? In about 2 decades, astronomers are hoping somebody, namely NASA, will be able to build a new telescope that can see them.
And how big would that telescope have to be?
About the size of Webb, 6 meters across, only more perfect.
Okay, very cool. So kind of talking about the size of telescopes, I've been doing some research, and so JWST has a massive 6.5 meters or 21 feet 4 inches. And then you compare it to Hubble, which is 2.4 meters or 7 feet 10 inches. And then there's that viewing power, which is significant. But then you turn around and look at a telescope on Earth like the Giant Magellan Telescope that has a mirror that's 25.4 meters or 83 feet 4 inches, which is 4 times more massive than JWST. Outside of the obvious that you have to deal with light pollution and weather and the elements that are out of your control, what are the pros and cons of creating telescopes like JWST when you have projects like the Great Magellan Telescope on the horizon?
Okay, well, of course, the reason to build a space telescope is to do something you could never do from the ground. So what is it you can never do? Well, certain wavelengths of light will just not go through the atmosphere. It's just opaque. Or some wavelengths of light are emitted very strongly by the atmosphere, so that you're looking through a glowing cloud. So if that's what you need to do, then you cannot do it from the ground. So when we said we're going to build the Webb, that's what we chose. Do things you cannot possibly do from the ground. Because, of course, we knew in advance that big telescopes on the ground would be built, like the Giant Magellan. And so fully expecting that to happen. Hasn't been finished yet, but they are coming. So on the ground, you do everything you can through the atmosphere. So if you can do it from the ground, you can do it sooner, a lot cheaper, because space projects are not cheap.
No.
They are getting cheaper. Because we're doing a lot of them and we're learning how, and the technology is improving. So if we had started off to build the Webb when we started to build the Hubble, it would have just been completely impossible. Now we can do it, and there will be generations of telescopes after the Webb that are much more powerful. But in the meantime, do everything you can on the ground.
Okay.
So it's totally gigantic telescope in the ground. The biggest one we're currently building is called the European Extremely Large Telescope. It is 39 meters across.
Jeez.
So almost the width of a football field. It's covered with lots of glass hexagons.
Okay.
And they got enough money to build it.
Wow.
So coming in a few years, we should get pictures from this giant telescope, and it'll be working. So I'm jealous.
What would it take to make a telescope the size of the Giant Magellan Telescope at a Lagrange point like JWST?
Well, the sort of general idea is, well, you need to get a lot of mirror up there. So either a lot bigger rockets or a lot better way of folding up things to get into the rockets we have. So both are coming. Elon Musk is building bigger rockets. We hope they work. And so people have made lots of drawings. I have already drawings about how to do a 40-meter telescope in outer space that is assembled by its own robots.
Wow.
We know what we would have to do, and it's not impossible. So when the time comes, and if that becomes the top priority for astronomers, they say, well, that's what we have to do. That's what it takes to solve the next big problem. Then maybe we get to do it. So right now we're smaller steps, but it's not impossible. It really is not impossible.
Cool. No, I love that. And I'm so excited to see what in my lifetime, the telescopes that come out of projects like JWST. Coming up next, we're going to be talking more with Dr. John Mather, the senior astrophysicist for the James Webb Space Telescope, here on The Space Between.
Hi, my name is Ryan Gilbert. I'm a former sports broadcaster for Wildcat 91.9, K-State alum, and basketball recruiting editor for GoPowerCat.com. The last academic year was a historic one for the station, as Wildcat 91.9 was named the best college radio station in the nation by the Intercollegiate Broadcasting System Awards, the first national championship in program history. However, despite all the awards and success, the budget for Wildcat 91.9 continues to be cut year by year. I'll be perfectly frank with you. Either Wildcat 91.9 finds new funding through charitable giving, or it will permanently go off the air. That's why I'm asking you today to consider making a tax-deductible contribution to the station so that the longest continuously running college FM radio station in the nation can continue to train the next generation of media stars. To make a contribution or discuss options for creating an endowment fund, please reach out to us at www.wildcat919.com/donate. That's www.wildcat919.com/donate. Thanks so much. Go Cats, and always remember that at Wildcat 919, you belong.
Welcome back to The Space Between. Kolby Van Camp and Dawson Wagner sitting here with Dr. John Mather, the senior astrophysicist for the James Webb Space Telescope. Just an honor to have you on the show. And we've been talking about the size of telescopes that we can put out into the Lagrange points that are between Earth and the sun. And now I'm curious because a friend of the show is a professor at Columbia University. You might know him. His name is Dr. David Kipping. He runs the Cool Worlds Lab, and he wrote a very fascinating paper and did a really cool YouTube video about an idea that he had called the terrascope, which is where you use the light that reflects around the sun, and you can find it at a very specific point at a distance from Earth, a couple astronomical units, and turn the Earth into a bit of a telescope, and he called it the terrascope. Is something like that feasible, or is that just theory and principle at this point?
Well, right now it's theory and principle, and it's really exciting to see people work out what you would do. So maybe I should explain more of the detail about it and why it could possibly work.
Sure.
So Einstein told us back in 1916 that gravity works by bending space-time. And that means light going by the sun is deflected a little bit. Okay, well, what if you did that on purpose? And suppose you put your telescope over there and the sun in the middle and your target way over there on the other side, and you just position everything exactly right. So now you have a ring around the sun of where light is focused just exactly right to come from that distant object over there. So in principle, now you could make an image of the surface of another planet. I mean surface, not just that it's there, the actual features of the surface, if you could put your equipment at the right place. But when you said a few AU, it's actually more like a few thousand AU.
Oh, really?
So this is a really hard thing to do. You have to get your equipment way, 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 way far away from the sun.
Sure.
So then you have to send back the signal. And it has to work because we're not going out there with it. So this is a good engineering challenge, and it'll take us a long time because the equipment that we currently can conceive of would take forever just to get to that place, much less make an observation. So it's worth thinking about. Things that are not impossible, sometimes it's worth thinking through, and the technology will develop.
Cool. I love that. Dawson, go ahead.
Yeah, thinking about things that maybe are more closer within the next few years, some missions that I've seen, the Artemis missions going back to the moon. How feasible would it be to, maybe utilize the moon and being able to set up a telescope there instead of sending it up into orbit and having to have robots, put it together there, and instead using the surface of the moon as a point to be able to observe things? Is that feasible? Is that something that, is possibly in the works or would be, beneficial to
well,
observing?
good question. There are a few things for which the moon is the best place to go. And so why would moon be the best place to go, considering that it's hard to land there and it's got dirt on the surface and night and day and all that? The far side of the moon, when it's dark over there, that is to say, when the moon is full here, it's quiet for the radio waves. It's protected on the far side from noise coming from the sun. It's protected on the far side from noise coming from the Earth. So if you want the quietest place in the entire solar system to put a radio telescope, that's it. So what you're going to do when you get there, it's to be determined. Again, we have to start with doing everything you can on the ground before you try the moon. Other things are harder on the moon than in space. So why didn't we put the Webb telescope on the moon? Because the moon does not help. You have to withstand landing, and then it has to work again. So it's hard enough to put it in space, much less to get it to land again. So also, maybe people don't fully appreciate the dirt that's on the surface. The surface of the moon is covered with tiny crystals of broken up crystals. So where did they come from? Interplanetary dust grains. Sand grains fly through the space at 30,000 meters per second. And they crash into the surface of the moon and they disintegrate and turn into shrapnel. So you go out and put on your boots, your space boots, and you come back into the house, you are covered with this really nasty kind of dust. So it's not an unsolvable problem, but it's a tricky one. So it makes it hard to plan to be an astronaut. Of course, we did it, but getting the dust off your boots is hard.
Right.
That's cool.
And maintaining a civilization there, or some sort of place where they would set up camp. I know that's part of the Artemis missions. Have you looked into the Artemis missions? I'm just curious on what your opinion of going back.
Not very much. I read up about them, but I am not tracking the details. Of course, the dust problem is something you could solve if you could put down a carpet or something across your part of the moon. So people are obviously working on this problem.
Sure. Would the moon's atmosphere be conducive for something like a giant Magellan telescope because it has such a thin atmosphere and you get more of that infrared light?
Actually, the moon has almost no atmosphere at all.
Okay.
It's very hard to detect what's there. What we do see is the dust grains are bouncing up and lifting off the surface maybe a few inches. So that's a kind of atmosphere, but it really doesn't do anything except get in the way of your boots.
Okay, so then it would work then, is what I'm hearing? Yeah. Okay. Awesome. No, I love that. That's really cool.
Yeah, I was just interested from studying the missions and the things that you mentioned, like Starship, and the ways that maybe we could send up larger satellites and things one day. Do you track satellites and things that we're currently launching through Falcon Heavy and different other self-landing rockets that are able to allow us to then send up more things to be able to study through the use of satellites and in space?
I don't track very many of the details. I'm interested in the things that are opening up that would make a possibility for some of my new ideas. Yeah. And of course, all of us astronomers and NASA people are thrilled when somebody makes a new, better, cheaper rocket. So we see that. We're all thrilled to see that Elon can land his rocket boosters backwards down on the ground and use them over again. And so we love that. We hope has good luck with his Starship because it's bigger, it can carry bigger telescopes. So we'll see. We wish he has good luck. As well, anyway, we depend on having good rocket launches. In the end, though, they are not they're not the expensive part of a mission. They're kind of routine. You say, send the company a check and they'll send you up. So it's also pretty remarkable. It is routine. it wasn't so long ago. That didn't work very often, and now they almost always are perfect.
Wow.
So
it's a testament to the ingenuity of humanity in the way that we continue to develop new technology. And like you said, things that weren't routine just 30, 40 years ago are now routine today. And we're getting to a sci-fi age where my grandmother looks back, she's 99, and she looks back and says, gosh, I was building parachutes to put on buzz bombs to drop on Hitler in World War II. That was my first job. And now we have these telescopes that can see into the dim and distant past. That's pretty remarkable.
Yes, and I was thinking about that too. I was watching Jack Kennedy's speech, announcing that we were going to the moon. And he said, 35 years ago, we flew across the Atlantic. So we had just barely invented airplanes.
Yeah.
35 years before we said we were going to the moon. And can you imagine the nerve and the ambition that it took to do that? And then that was in 1962. In 1969, they actually landed and walked around on the moon and had to dust off their boots.
The context is really cool.
Miracle of modern organization and technology. And most of the people calculating things, they used slide rules.
Oh man, when we talk, Dawson and I consider ourselves to be communications scientists. We're getting master's degrees in mass communications, and which is why we do this podcast, because we love science communication. It's a passion for us, and so being able to contextualize that kind of information and communicate it to people of just how remarkable it is, I think is really important. So I appreciate you bringing that up.
Yeah, and well, thanks also for working on science communications. People don't understand what most scientists say.
we try to help.
We need people to help us.
Yeah, we try to help. We're not scientists by any stretch of the imagination, but we try to do our part. Out of curiosity, do you have a picture from JWST that you say that's the picture that I love the most? Is there one that stands out to you?
Yeah, I still love the one we chose for Joe Biden to announce. And it's a picture that shows a few stars, a few gigantic galaxies, and then all these funny, weird-shaped arcs, pink arcs, which are images of much more distant galaxies that were magnified by Einstein's lenses. When I told you that gravity bends space-time, well, it can magnify the image of an even more distant galaxy. So we've got dozens of those highly magnified images of very distant galaxies in that one picture. So when it just captures the whole sense of adventure of looking back in time as far as you can possibly go, and there's some big surprises in those little pink arcs.
That's super fun. I love pictures like that. Dawson and I are astrophotographers here on Earth in our spare time. It's a hobby that I have, and it keeps me grounded and connected. For some people, it gives them an existential threat. Like they look at the sky and say, oh my God, there's so much stuff and I can't handle it all. To me, it's therapeutic to go outside and look at the heavens. I just love all the pictures that JWST is taking. And I especially love that you talked about at your speech here at K-State that there's just some random lady on the West Coast that's processing your images. You send her all of the data and she processes it and then spits out these incredible photos back to you. Can you talk about her and her work a little bit more?
Yeah, so she's not a random lady. She's a special lady.
I misspoke there.
The art of, yes, anyway, I know, I'm kidding. She's mastered the art of taking pictures and making them show what you want to show.
Yeah.
So, for instance, we've got a picture of a galaxy that looks like it's sliced through a sponge. So she was the one who made that very clear. You adjust the contrast, you adjust the color, you do adjust a few other things so you can show the message that's in the picture. So she does that very beautifully.
Yeah. And there's an art to it. It takes a lot of skill to be able to see things in an image and say, oh, if I adjust it just a little bit this way, then that's going to pop out, or we need to look at this particular wavelength of light to expand some of the images. You can do that on Earth, and I'm looking into doing narrowband imaging in my own astrophotography. But could you talk about the way that you do that kind of imaging with the James Webb Space Telescope and how it creates what we call the Hubble palette now in the images that we have?
Yeah, we can say a little bit about it. Of course, we built an infrared telescope, which means it picks up light that you can't possibly see. So we have to do something to give you an artificial color. So what we usually do is put the colors in the same order that you would have. Short wavelengths blue, medium wavelengths yellow and green, long wavelengths red. And so that gives common sense. So an astronomer or a member of the public can say, well, that's probably about what it means. Hot things are blue, cool things are red, typically in astronomy. So that gives it meaning. Once in a while, we do it another way, because we can have, as you mentioned, narrowband filters. We can have a particular color filter that says, I'm only picking up the light from oxygen. Okay, so then we can make you a picture of where all of the oxygen is. So to show you that, well, maybe we'll make it green. So everywhere you see a green thing, that's a oxygen something.
Sure.
So we have our ways to try to make sense, both visually and scientifically, of the pictures. So we're scientists, and we don't know what we're looking at either at first. So we have to look at these things that make sense, find the patterns that nobody ever noticed before, and say, this is what that means. So we use color, just as you do, to find the things that mean something.
Yeah. I especially enjoy looking at the images where you can see the oxygen and the hydrogen alpha and the sulfur 2 that most people are trying to filter out and then restack in the post-editing process, which I think is really fascinating. So I'm going to switch gears for just a moment here, because Dawson and I just recorded an interview with Betty Maya Foote, and she is an individual who is an advocate for the Dark Sky Initiative, and it's a program that reduces light pollution around the world. Is that a necessary thing in your mind, to reduce the light pollution around the world?
Well, I certainly think so.
Okay.
I'm a member of the International Dark Sky Association myself.
Good.
I think I'm a life member.
Good.
Because in my lifetime, we've lost the ability to see the stars in many parts of the world. So we turned on the lights. It's nice to have lights. We feel safer, but we turn them on so much that we've lost something. So why do we care? Well, astronomers care because we like to see. The public, I think, needs to see just to have some idea where it is that we live. The night sky is beautiful if it's not just clouds. So we think we need that aesthetic. We need that feeling of connection to the sky and to the rest of the universe. You can only get if you can see it. Then there are much more practical effects, that if the sky is too bright, some things change in our bodies. We don't sleep as well, or our hormones are different, or wild animals or plants don't migrate, or they don't grow right. So it's to all our benefit if we can manage keeping the sky dark at night. It's not so bad. It's not so hard. Mostly it means point the lights downwards. Don't point them upwards. That's pretty easy.
Yeah.
But it's and it saves money as well. So
it saves a ton of money.
Do this. Yeah, saves a ton of money. There's no reason to point your light bulbs up when you're looking down.
So as we begin to wrap things up, I'm going to give Dawson his last question, and then I'll tee off with my final two, and then we'll get you out of here. We appreciate your time. Dawson, go ahead.
Okay.
Well,
Yeah.
I've just been begging to ask about what you think about the Fermi Paradox, and if life is out there, what are some things that you kind of lean towards on the side of whether there is or isn't aliens, and maybe some things about that the government has talked about recently that you could maybe talk about yourself, if you have any knowledge on that subject.
So sure. Well, what's the Fermi Paradox? Fermi asked in the late 1940s, what if there are alien civilizations? Where are they? And his sort of basic question was, if they're sufficiently technically advanced, couldn't they travel here? So there's an ingoing assumption there, or a guess, that space travel over immense interstellar distance is possible. And so, well, So what do we actually see? We have no sign whatever of credible evidence of anything from any other planetary system here. We have one wild thing that came flying through the solar system a few years ago called Oumuamua, which is a Hawaiian word that I've forgotten the meaning of it, but basically it's an interstellar comet. Some little chunk of another planetary system came flying through our planetary system, and we said, that's pretty unusual. Of course, some people would say that must mean it's inhabited by aliens, but I say, no, there's no sign of that. Too bad. I think it's actually kind of disappointing because many of us grew up on a pretty steady diet of science fiction stories of interplanetary and interstellar travel of all sorts. And so why aren't they here? Well, I think the number one reason is it's too dang far. If we used basically any of the tools we have today to travel to another planetary system, around another star, take 100,000 years to get there, more or less. And we're not making the trip as individuals. You might make your trip in frozen animation. You might send a robot to do your exploring for you. But if you send a very intelligent robot, the robot could say, I'm bored. I don't want to make that trip. So we have this interesting problem about time. It's just too darn far between stars. Here, there are places in the galaxy where stars are a lot closer together. So maybe in those places there could be interstellar travel, but not here. So that's the sort of situation we're now in. We don't have a way that we can seriously imagine to get from here to there. So, but there's another part of the question is, could anybody be out there, even if we can't see them or get there? And so I think the short version is we think so. There are going to be lots of candidate planets. Most stars have planets the right size, and some have right size and temperature. About the size of Earth, about the temperature of Earth. So there are a lot of potential places to go. And imagine somebody's out there. So then you get to the question of, well, is life common or rare? So when I was a kid, most scientists, most philosophers had come to the conclusion that because life is so complicated, it could not possibly arise without an extremely rare event, some extremely unlikely event, or divine intervention. So today, however, mood has shifted because we're recognizing that things organize spontaneously into complexity. And thermodynamics is not against it. Thermodynamics actually favors complex systems. You and I are increasing entropy in the world by being alive. So I think we no longer can say that it's an extremely unlikely event. We just don't know. So I'm guessing the opposite. I think, as a guess, that life will always occur given a chance.
Okay. That's a great stance.
How would we know? Have to go look.
You have to go searching for it. So I have a silly question, and then I'm going to tee off with my final question. And my silly question is,
okay.
You're clearly a man of style. Dawson and I enjoyed your Pillars of Creation tie that you wore at your speech here at K-State just a couple of weeks ago. And I have to know, Crocs and socks, does that work? Is it a good fashion statement, or should you just no? Absolutely not.
Well, I don't know about Crocs and socks, but I'll tell you what I do wear. I wear sneakers, gray sneakers with tan socks and tan slacks. So
okay,
people can't see that on the video, but I'm a creature of habit.
Well, somebody that has as much as they're doing as you probably needs a little bit of habitual clothes wearing in that way. So that makes a lot of sense. My final question for you as we wrap up the show is, I'm sure you could get access to any telescope in the world if you just asked. Do you capitalize on that? Do you like to go outside and just spend time outside looking at the sky?
Actually, have not taken much advantage of that. Certainly when I go visit a friend who has access to a telescope, they're happy to show it to me.
Cool.
But in truth, access to a big telescope is precious. So we don't want to waste it on John Mather wants to look through the eyepiece. We want somebody who's going to use the time to do something, to discover something. So, yeah, I don't actually ask to look through big telescopes, even though it would be fun.
Yeah, that would be fun. Well, we're hoping to set up some opportunities to go and travel to some smaller telescopes and observatories around the United States and record on location and interview some people. So that's coming down the pike for the show. But that's really cool. I just love being able to go to a place and look at the skies like that.
So let me mention one that's not so very far away from you. Your Case Observatory. It's in Wisconsin.
Okay.
It's was the first giant telescope in the world. It was built in 1897.
Wow.
Has a 40-inch diameter lens, which was enormous. It's still there. It's no longer very scientifically useful because it's not exactly the best astronomy site, and it's not very big in relative terms anymore. But it's just been turned into a public facility for the neighbors and visitors and science nerds to come visit. So it might be a good place for you all to pay a visit to.
Oh, yeah. No, that'd be really cool. We'll have to look into that as soon as we get off the show. We'll just have to start Googling and asking around. Well, Dr. Mather, it's been an absolute pleasure to have you on with us today. And you're hopefully the first of many, but still, you hold a special place in our hearts for being one of the first true major scientists to come on the show. So thank you from the bottom of our hearts to you for taking time out of your day to speak with us.
Well, thank you, Kolby. Thank you, Dawson. It's a great pleasure to talk with you and to see you. And this is an amazing technology that we're using. But thanks also to so many other people behind the scenes who make this all possible.
Absolutely. Thank you to them indeed. We appreciate you tuning into the show. As always, give us 5 stars on whatever podcasting form that you are listening to, or subscribe to us on YouTube. You can follow us on social media, Facebook, Instagram. I made a TikTok last night against my better judgment, so we'll see how that works out. And if you want to check out all of our information, you can go to www.spacebetweenpodcast.com. My name's Kolby Van Camp here with Dawson Wagner and Dr. John Mather, and you've been listening to The Space Between.